First, I'd like to thank the organizers for inviting me to give a talk here. So, I'm Kaustuv Manna. I work in Max Planck Institute Dresden with Professor Claudia Felser. So, today I'll talk about our recent experimental results on the new fermion stuff. But I'd like to first thank to Niels for giving a nice introduction on this work, and I'll just give a little bit extra overview whatever we did. But I'll try to wrap up a little early because at the end I want to talk a little bit about a different topic. So it's on magnetic wire semi metal. So today we are very excited. We have 3 papers in Science came out online. So I just want to give a brief introduction, and if you are interested, we can discuss later in detail anyway. So this is just we started working on this topological chiral crystals in 2017 when these 2 papers appeared in PRL, and so this overview, like in the gamma and the R point, you should have the new fermion like 4-fold and 6-fold band crossing. So in the high symmetric points. Now once these predictions came out, then I have grown a series of single crystal on these all belong to the same symmetric B20 chiral crystals. And of course, depending on the phase diagram, I had to tune my crystal growth technique, and then with from flux to self flux to breach band to chemical vapor transport to obtain these crystals. And, but I just want to tell you one thing, that the same crystal, it can be grown in different techniques. For example, this chromium, for this cobalt silicon, it can be grown in CVT or flux or breach band, even optical floating zone. But even though it's a single crystal, all case, the quality of the crystal is very, very different. So you need to tune the crystal growth technique to get the best crystal for your experimental results. And out of all these crystals, so this particular sample which we are discussing with about in Niels talks, this is not actually a single crystal. So this has big grains, like 300 to 400 micron grains. So it has 2 things, advantage as well as disadvantage. Disadvantage is that it's not a single crystal, but it doesn't make any problem for the RPS experiment, as you saw in Niels talk. But the advantage here is that here we have the grain boundary between the different chiral crystals. So right now we are investigating some fancy STM experiment to see at the grain boundary what is going on in different chiral crystals. So, but this is an ongoing project. So next I just wanted to talk about these 2 opposite chiral crystals in Niels' talk. So these different crystals, so I have grown using the seed. So this seed is cobalt doped iron silicon. So it's already shown in literature that until 10% cobalt doping, this is a left-handed chiral crystal. Whereas if you increase the cobalt doping, say 25%, then it forms a right-handed chiral crystal. So first these single crystals are grown, then these are used as a seed to do this forced crystal growth for opposite chiral crystals. So as you say, so we after growing the crystals, so it looks somehow the bad, but it's not bad quality crystal because we clearly see the RPS and we see quantum oscillation, very nice quantum oscillation in these crystals. So indeed these crystals are very good quality. And we use the X-ray absorption spectroscopy to determine the structural chirality of the sample. And so from this Wyckoff position, just crudely you can understand that the Wyckoff position of the PD and G are simply opposite. So these are 2 opposite chiral crystals. So we have done different characterization of these samples. So of course RPS for all these crystals, and as Niels has discussed about the RPS result of this particular platinum gallium and the palladium gallium case. So I'll not go into the result discussion for this section. So I'll just discuss mainly focus on these 2 parts. So like what is the effect of strong spin orbit coupling on the band structure of these new fermions, and second is the CPGA results on rhodium silicon. So just give an overview, whatever Niels was discussing the new fermions in aluminum platinum, similar thing we have observed in cobalt silicon also. We have observed the new fermions, and this is the surface state. So there are these helical Fermi arc wrapping around this high symmetric momenta, and this is for rhodium silicon case. The same results, as you see, there are this Fermi arc wrapping around this high symmetric momenta, and this is experimental result. So this is done in collaboration with Professor Jahid Hassan. And now point is that all this cobalt silicon and rhodium silicon, we could not resolve the Fermi arc because of the weak spin orbit coupling. But since the Chern number is 4, of course we should have 4 number of Fermi arcs in the system. So for that, what we wanted to indicate is that maybe if we enhance the spin orbit coupling in the sample, maybe it will be coming in the help. So for that, we focus on this particular compound, which is this platinum gallium. So this compound has the strongest spin orbit coupling in this entire series of these chiral crystals. So this is the band structure of the platinum gallium, and you see the effect of spin orbit coupling here. So this is without SOC, and this is after incorporating SOC. What happens? So all the bands, it's strongly split. So this is the color code which shows how the bands split. So this blue line, it splits into blue and green, and it holds true for the all other bands as well. Now this is on the bulk band structure, but if you see on the surface state, so this is the Fermi arc of this crystal. As you see, there is giant spin splitting of the Fermi arc. So this is like largest splitting of what we can imagine of in this entire series of crystal. So we thought that if we do the experiment, maybe this much more easily we can realize this splitting of the Fermi arc in these new fermion systems. So for that, of course, we need to do RPS, but that is one technique. Another technique is that we can realize this spin splitting of the Fermi, this Fermi surface by in the lab itself. So that's by quantum oscillation. So we do the quantum oscillation investigation to investigate this band splitting of this sample. So for that, first criteria is to grow very good quality sample. So I have tuned the crystal growth, and finally I have the crystal with very high RRR value. So if you see in literature, the chiral crystals, the reported crystals have RRR not more than 20 or 30. But this case we could achieve RRR up to 84, which is very high. And we can observe very high anomalous, MR until 1000 parts in this compound. Now this is a quantum oscillation, so we clearly see quantum oscillation until say 7 Tesla, and of course it's and if we zoom in, you will see that the quantum oscillation starts with 0.5 Tesla itself. So it's very high quality single crystal, and we observe the quantum oscillation up to 15K. And this is at different directions. When you apply magnetic field, you see that the nature of the quantum oscillation is quite different. So it's a highly anisotropic Fermi surface. Now to understand the effect of the band splitting, so what we need to look is that the FFT of this, and we check, we compare the frequencies of from the FFT. So this is the FFT of at 2 Kelvin of a particular magnetic field along 1001 direction. So of course there are a lot of frequencies, because if you see from the band structure, there are a lot of Fermi pockets coming because of the different band splitting of the SPONG SOC. And this is the overall the total Fermi surface in the full Brillouin zone. So it's a very complicated scenario, as you understand. So just for simplicity, we focus at gamma point, what is going on at the gamma point. So at gamma point, from these two bands, these two spin split band, it gives rise to near spherical Fermi pockets. So these two, this red and the blue ones is coming from these two bands, and other two bands give these two kind of this complicated this spin split Fermi pockets. Now once we compare this theory with the experimental result, we could very easily identify this alpha 1 and alpha 2 experimentally. Then for the other two Fermi pockets, when you want to compare, there are actually three extremal frequency. One is at this point, another was inside, but they are supposed to be on the top also. And this frequency is very, very high. So as you understand, so as we go away to the higher and higher frequency, the theory and experiment deviates from each other. So that's why we try to focus in the low frequency region and compare theory and experiment. So we could clearly identify these two frequencies, beta 1, beta 2 and gamma 1, gamma 2 in the experiment. And we clearly observe very large spin split of nearly 190 Tesla in this compound. Now next is the RPS experiment. So this is our very preliminary RPS result. So at a particular 67 eV, so this is the RPS the spectrum. Now if you want to compare with the bulk, what we found is that the theoretical calculation, not only simple bulk, but bulk plus surface state combined, it matches very well with the experimental result. So whatever feature we observe is predominantly coming from the surface state only in this material. Now next is we want to look into the Fermi arc, what is happening at the Fermi arc, whether we can look at the spin splitting or not. So these are the two Fermi arcs at two different energy, 67 and 23 eV. So both cases you see that this is the Fermi arc which is helically wrapping around these two high symmetric momenta, and at this particular cut you clearly see there are two Fermi arcs. So data quality of course is not good, we are right now improving the data, but still it's the clear message that we have the splitting of the fermion. So this platinum gallium is the second example apart from palladium gallium, whatever Niels was showing. So both of these cases we clearly see the splitting of the fermion. So there are 4 number of fermions which is coming from the chart number 4 in this new fermions. Now next is the practical application, that's the CPG effect. So I am very thankful to Fernando for giving very nice introduction for this origin of the circularly polarized light like effect in the white semi-metal. So just to give a conclusive remark, like once you apply the circularly polarized light in a white semi-metal, so the rate of current generation is this much, which is independent from any material specific parameter, and it's directly proportional to the Chern number of the compound. Now since in this white fermion we have Chern number 4, we should expect 4 times larger current compared to the conventional white fermion. But if you do this experiment on a conventional white, you will never observe this effect. That is because we have a mirror symmetry, and due to which these two Chern number, it appears at the same energy. So the current generation from one oil, it will simply nullify the other. So at a net result, you will never observe the quantized circular photogalvanic response. So at this point, this chiral symmetry of this new fermions, it comes to our aid. So here instead of the mirror symmetry, we have this glide operation. So mirror plus mirror reflection plus translation. So because of which these two opposite Chern number fermions, it forms at 2 different energy. So if somehow we can block one oil fermion, then we might observe the circularly polarized response due to the other oil. But so far I discussed a lot of chiral crystals. So which of the crystal is the most suitable one for this experiment? So for that, if you just look in the band structure, for palladium gallium or platinum gallium, these two particular case, it's very bad for this experiment. That's because, you see, there are a lot of other bands which is crossing the Fermi level. So even though you have this CPG effect, it will simply get masked. So there is no point of trying for these two samples. So these two crystals, rhodium silicon, are the best candidate. But cobalt silicon case problem is that this Pauli blocking energy is very small. It's merely 0.3 or 0.4 eV. So the rhodium silicon is the best candidate because here Pauli blocking is merely 0.7 eV. So it is much better for this experiment. So this is our first experimental result which is there in the archive. So it is many times it's shown in this workshop. So as you see, there are 2 important features is that so above 0.66 eV there is a kind of a breakdown of this current generation, and below of this 0.6 eV it's nearly quantized. But as Fernando was telling, this is not actually quantized effect. That's because there are 2 major problems here. One is that if you see, the net Chern number is not 4, which we should expect. That's one thing. Second thing is that this lot of noise is coming because the tau, the momentum relaxation time for this sample is very, very small. Okay, so that that maybe there may be different origin, maybe intrinsic or maybe extrinsic. Extrinsic means maybe there is a defect which is playing a role here. So for that we are improving the sample quality if we can increase tau, and we can have better experiment. But just to understand what is going on, so just look at this band structure. So until 0.66 eV, what happens here is that the moment you the circularly polarized light, the electrons it excites from the valence band to the conduction band, but until this much energy, this conduction band is already filled. So there is no way that this valence band can go. So that's why until 0.66 eV, this wild fermion is Pauli blocked. So whatever result we are observing is purely from the gamma point. But our recent result, so once we did the experiment, repeat the experiment on a better quality crystal, slightly better, what you observe is that now noise is slightly reduced, but you see it's not exactly quantized. There is a certain frequency dependence until 0.66 eV, and this breakdown effect is obvious. Because higher this energy is obviously once this wild point gets active, it will simply nullify the effect, overall effect. But below 0.66 eV, what happens is that you have the quantization effect coming from this gamma point, but the gamma point is not the only one which is contributing. See, there is a finite dose at M point also. So the moment you put the circularly polarized light, you have excitation coming from the gamma point, which already increased the current very high, and on top of that you have a frequency dependence coming from the M point. So that's why it's not fully quantized, but you have a kind of this hump kind of effect. But overall, from digital aspect point of view, you can think of like it's kind of like quantized and its breakdown happens. So this is our latest result, but we are of course improving our sample quality to have better insight in this. But this is right now we have.
So in addition to the low frequency features, it went down by roughly 4 compared to the previous one?
Sorry?
So
No. See, that's why here E cubed by H square, so this is already 1/3. Okay. So if you count back to Char number, okay, still it is 3 point something.
Okay.
3.5. It is still there. Okay. So that's why I just saw beta tau, and I saw here the 1/3 is term is there already.
Yeah, because you only do one component.
Yeah.
Why 3.5?
See, if you see here, that's why 1/3 it is there plus 1 point something. So you have to multiply this with 3 to get the Char number. Okay. So we are still working on this to improve the data. But next, I want to move to the next topic, which is the magnetic wire semi-metal. So we are very excited today. We have these 3 papers which came out in Science, and all of them we are discussing the first observation of wire fermion, magnetic wire fermion in nature. So as you know, the wire fermion can form because of 2 reasons. One is the broken inversion symmetry or broken time reversal symmetry. But time reversal symmetry broken case, if you see the inversion symmetry broken, there are a lot of examples from tantalum arsenide to niobium phosphide, where it's already shown that inversion symmetry broken wire fermion is already reported. But in 2016, these 2 papers came mainly from the Barnavik's group and Zahid Hassan's group, where they predicted that this time reversal symmetry broken wire fermion maybe we can realize in cobalt-2 based full Hassler compound. And this paper, when came out in 2016, we were already doing the experiment in 2016. So our experimental result, whatever I show, is actually done in 2016. It took nearly 3 years for us to convince the editors of different journals and different referees to put the paper in Science. So, but anyway, life is hard. So at the end, we have the paper. So, okay. So to start with, this cobalt-2 manganese gallium. So this compound is a full Hassler compound. So it crystallized in FM Barchian space group, and this is the atomic arrangement. So in the band structure, you see we have a band crossing very close to the Fermi level, and this band crossing, it leads to a nodal line which is protected by this particular mirror symmetry. And in this compound, you have these 3 mirror symmetries Mx, My, Mz, which is because of this, we have 3 nodal lines protected by this 3 mirror symmetry. Now what is this nodal line that you can visualize from this picture? So let's consider you have a band overlapping, and this yellow region is just the common crossing point where this band overlaps. So this yellow line is the nodal line. So in this compound we have 3 nodal lines which are protected by this particular mirror symmetry. Now this picture, whatever I discuss, is without spin orbit coupling into consideration. Now if you consider spin orbit coupling into account, then spin is no longer good contour number. Then what happens is that the crystal symmetry reduces depending on what is the direction of the spin. So let's consider we apply the magnetic field and polarize all the spin along the z direction. Then what happens is that these 2 mirror symmetry, then Mx and My are no longer mirror symmetry of the system. So if the mirror symmetry once breaks out, there is nothing to protect this band crossing. So of course the bands also gaps out. But the MZ is still the mirror symmetry, because of which this nodal line which is lying at the MZ is still protected. And the moment this nodal line it opens up, it gives rise a very strong contrast of the Berry curvature. Now this Berry curvature, it has direct connection with the physical properties. For example, we do anomalous Hall conductivity experiment. So anomalous Hall conductivity is simply the integration of Berry curvature for all the states up to Fermi energy. So if you have a strong Berry curvature contrast very close to Fermi level, immediately we should expect very high anomalous Hall conductivity in the sample. So first we want to do experimental verification whether these nodal lines, whatever theory predicts, is at all there or not. Then I will discuss about the transport properties. So this is, I have grown the single crystal using Bridgman technique, and from the magnetic characterizations, what I found is that this compound at room temperature, this is a ferromagnet with a very high moment, nearly 4 MeV magnetic moment. Okay. So in this room temperature ferromagnet, now we are doing the RPS experiment. So this is our theoretical calculation, and this is a schematic diagram where I am showing that these two bands are crossing, and this red line is actually the nodal line. And in the theoretical calculation, we have seen that this compound has a network of nodal line. There are three types of nodal line. So this red, blue, and the yellow line, and this is a very complicated network. But once we measure the Fermi surface, you see it's a very complicated Fermi surface. But all the features, whatever Fermi surface shows, it can be exactly reproduced with the DFT calculation. For example, I just show you the features. So this red, blue, and yellow. So these are actually part of this nodal line which we see in the Fermi surface. Okay. Now I look into this different Fermi curves, so these different curves, and show it here at the dispersion. You see that there is a protected band crossing for a range of Ky values. So this is a distinctly different result compared to the conventional Weil or Dirac fermion, because for Weil or Dirac you should expect crossing point at a particular K value. But here, since for a range of K value, we observe the crossing point, so whatever feature we are looking at is actually a nodal line. Okay. Now we are looking at this same Ky cut at different binding energy. So the above, and so once we optimize the binding energy, say once we hit the nodal line, we have this dot-like feature. But above or below, once the nodal line it opens up, like the band crossing it opens up, like upper cut or ground part, immediately you see this feature is simply opposite. So whatever feature we are observing here, so this clearly tells that for the first time in this room temperature ferromagnet, we are observing the topological state. Now what is the consequence of these topological states on the physical properties? So for that, we want to measure the anomalous Hall conductivity. So this is the experimental setup where I pass the current here and do the longitudinal resistivity measurement, and this is the Hall signal it shows in the vertical, these two spots. Now this is the temperature dependent of Hall resistivity, sorry, the longitudinal resistivity. You see the sample is metallic throughout the temperature range, and this is from the magnetic field dependence of the Hall conductivity. We estimate the anomalous Hall conductivity by extrapolating from the high field data to a zero field value. So this is the anomalous Hall conductivity for this material, and once we compare this with all the other compounds that is reported in literature, you see our compound sits here on the top. So there is only one material, which is this iron. It has larger anomalous Hall. Otherwise, cobalt to manganese gallium has second largest anomalous Hall conductivity in the literature. Now how anisotropic is this anomalous Hall conductivity? For that, I do the measurement in two different configurations. So one case I apply the magnetic field along 110, another case is along 111. But both cases, the anomalous Hall conductivity does not change that much. So this compound is it's not, anisotropy is not much. But it's not very surprising also, because this is, first of all, this is a cubic material. Second, it's a very soft ferromagnet. So the anisotropy is very low in this compound. But when you estimate the anomalous Hall angle, this is just the ratio of anomalous Hall conductivity with respect to the longitudinal conductivity. As you see, it increases with temperature. And you observe the highest anomalous Hall conductivity of nearly 13, sorry, this anomalous Hall angle of nearly 13% at room temperature. And this is the largest anomalous Hall angle, so in any of these magnetic Heusler compounds. Now next, we want to see how much is the extrinsic contribution in the sample and how much is the intrinsic contribution which is coming from the band of the Berry curvature from this compound. So for that, we plot this rho xx square versus the anomalous Hall resistivity, and these points, data points, are at each temperature. We take the data of the field dependence of Hall resistivity, and from the high field measurement we estimate the anomalous Hall resistivity, and we plot it at a different temperature. So from this slope, what we estimate is that the temperature independent intrinsic contribution of anomalous Hall conductivity, which comes from the slope of this plot. So the slope gives the anomalous Hall conductivity is nearly 1000, and from the RPS measurement we estimate the Fermi, like where is the Fermi energy, and from the theoretical calculation we just estimate how is the Berry curvature contrast, and the integration simply gives this theoretical curve which shows the net anomalous Hall conductivity in the sample. So our experimental transport data is here, and this Fermi surface lies here. As you see, everything is one-to-one correspondence. So the intrinsic contribution of anomalous Hall conductivity and the experimentally determined anomalous Hall conductivity is exactly matching with each other. So this is the collaboration that the high anomalous Hall coming from in this material is actually a consequence of the topological states very close to Fermi energy in this compound. So next, I want to go to the summary. So there are a lot of future prospect what we can do here. So one prospect is that, so I showed you the electrical transport experiment. Then similarly we can do thermal transport also. So we have done thermal transport of this cobalt-2 manganese gallium. So this is the result I compare with the different other compounds. And you see this is in the log scale. And in the thermal transport, we estimate the anomalous notched thermal power. And as you see at room temperature, so this value, whatever I compare for cobalt-2 manganese gallium is actually the room temperature value. So at room temperature, the anomalous notched thermal power is 7 times larger than any of the compounds ever reported in literature. And since the transition temperature is 700 K, and the value is still increasing, maybe you can have a look in this paper where we have reported this year. So we don't know where it will stop, but it's still increasing. So another aspect is that since the anomalous Hall angle is very high in this compound, so that clearly gives an idea that the topological protection in this compound is much more robust with respect to temperature fluctuations. So there is a potential application, like if we can make a 2D version of this material, cobalt-2 manganese gallium, and make a device like this, and so that you have to arrange the magnetization perpendicular, it should not have form any domains. Then because of this topological protection, you might observe quantum anomalous Hall effect, and since the transition temperature is very high, who knows, anomalous Hall conductivity may be protected at very high temperature. So we have discussed many of these future aspects in this review article. So we are you can just go through or you can discuss. So now I want to thank to all of my collaborators who helped me for different characterizations, and Niels is here, and I don't know, no, Barnamik is not here, but anyway, all other, thanks all of them, and particularly my postdoc supervisor, Claudia Felser. So thank you.
Questions?
The chiral crystal growth with the seed is super fascinating. Like, do you have any intuition for like why that this? So you mentioned this iron compound, but like why for some density it's left and other it's right? That's some weird
yes, that is a mystery actually. Yeah. Right now we are doing a systematic investigation. Like, see, because the thing is that I'm not chemist, so I just made one attempt. And it was successful, I just carried on. So now when I'm presenting the data, many people ask me this question. Yeah. So right now we are doing a systematic investigation. So whether it was an accident or it is a really systematic one or not. So now we have grown different batch of these cobalt systems, and we are doing investigation. But it's already in literature. It's already there. There is a PRB paper. Maybe I can show you. So where they shown that this left-handed chiral crystal is actually below 10%. It goes. Why it goes, yeah, I don't know. Maybe there is energy difference. I don't know. But why suddenly energy difference will come in this same crystal structure? Yeah, no idea.
But now you can grow, so that you can grow domains.
Not domain, actually single crystal of this cobalt doped iron silicon crystals. Then you can use that as a seed for your growth. Now depending on, there are different techniques you can grow the single crystals. One is the self-flux technique. So whatever I used is like, so I put the crystal, cut it in a kind of a cone shape. So I don't know whether, so you know DSC experiment, right? DSC furnace for measuring the melting temperature. Okay. So this crystal is actually grown in DSC furnace. Okay. So I used the cone shape because we wanted to grow the crystal in a cone shape. So we grow the sample in the cone shape. Then we use that in the bottom of the crucible. Now if you want to grow it, now the catch is that the sample which you want to grow, the melting temperature has to have very low compared to the seed, otherwise seed will melt. Okay. So now cobalt silicon, rhodium silicon, if you want to grow, it will never work because melting temperature is nearly 1500 degrees Celsius. And this iron silicon case, melting temperature is nearly 1300 degrees Celsius. So palladium gallium is much easier because palladium gallium case its melting temperature around 1000 degrees Celsius. So just melt it and you can grow depending on the temperature profile, or you can use the Joublalsky growth, so you can use that as a seed and pull the platinum gallium, sorry, palladium gallium from the melt, that also you can grow, or maybe this optical floating zone, you can use that in the seed and then you can grow the crystal.
So can you ever get regions of the different chiralities?
So far, the crystals which I have grown, the entirely it's a single chiral. It's a miracle. Like, because the second one you saw, it's like, it looks horrible, but it's a single chiral, because I have taken pieces from different region of the sample and all turns out to be of same chirality. So it's a single chiral, single crystal.
Actually, I have a follow-up question. So then you show that, so in this regard, like cobalt silicate, all of the cobalt silicate has one chirality, right?
Yes.
So is it left or right?
That I have to check. That I have to check.
Then what about rhodium silicate?
That's also single chirality. So that is, I think, right-handed. I have to check, but that is, I think, right-handed crystal. So until unless you do a forced growth like this, it's like in the, as my feeling, if the energy is same, then depends on like different batch should have different chirality. But within one batch of the crystal, should have single.
No, you have a one slide, so the iron cobalt silicon, right?
Iron?
You have a one slide that shows, yeah, this one. So you were saying that when
see this entire crystal. See, this is the seed of iron. This iron cobalt silicon. This is actually the seed, and this is the crystal.
Yeah.
Okay.
No,
So this entire crystal is single chiral.
Yeah. So here basically you're saying that below, when X is below 8%, it's always left, right?
Is always left-handed.
It's always
so you have
left. Yeah.
yes. So you have to grow two crystals, one with 8% dope, another one is 25%.
So which means that so the cobalt silicate basically X is 1, right? So which means all of the cobalt silicate is right-handed. So I was asking you, is that the case?
I have to check. That's a good question.
Then,
Oh, I'm sorry. No, you keep going.
so
Sorry.
then if X is between these two, so maybe you can in one sample you can find
Mixed chirality?
maybe.
Maybe. Quite possible. Quite possible. But I have to check. But yeah.
So we have a couple more questions. I think we can do all three, whatever. So do Bing Hai, and then you, and then Niels, and then I think after that we'll.
Yeah. Okay, about the APAS result of the cobalt-2 material.
Cobalt to minus gallium.
Yeah. It showed that, like, if I in previous talk or somewhere we talk, this chiral material we see, the Fermi arc has some chirality, some preferred direction, right?
Sorry, tell me once again.
I mean the surface states in general. If it's a chiral,
This compound?
I first in general. For example, this cobalt-10, this thing, you showed their Fermi arc has some preferred direction because it's breaking invariant symmetry. I'm asking here in the opposite result for this material, it's break. You claim it's break time reversal. What's the signature of time reversal breaking in this figure?
See, signature in the sense that this metal is already ferromagnet at room temperature.
Yeah, I know, but from Fermi arc, I can recognize there's something.
Fermi arc for this particular compound determining Fermi arc is very difficult, because see, the moment you for that you need to apply magnetic field. That is not possible here. First of all. Second thing is that it forms the domains with the internal magnetic field itself. Somewhere it will be have the Fermi arc, but for that it's experimentally determined is very impossible.
Okay, APAS average everything kind of.
But from the RPS, what we observe is that see this green part which I didn't discuss. So this is the drumhead surface state. So if you have a wild line, then you should observe this drumhead surface state from that. So we have actually observed drumhead surface state because we didn't apply any magnetic field. So we have the protected nodal line. And once you incorporate, ideally, once you incorporate SOC, the nodal line should not be protected. But this compound, the SOC strength is very, very weak, because of which the gap is very small, beyond the experimental limitation. So we observe the nodal.
Can I see the surface state from the experimental result?
We have
which
it.
way?
Maybe I can. I can show it.
Yeah.
Okay, could you show me the picture of single crystals? the beginning of it. I'm not sure whether I missed that information or not. Yeah, the next slide. So did you have any special reason to use the ion-doped cobalt silicon as the seed?
Oh, that's what.
Yeah.
See, we wanted to grow opposite chiral crystals to see, because see, right now understanding of the topological states is that the topological states are protected by the crystal symmetry. So if you tune the crystal symmetry, in principle, you should be able to tune the topological states, right? So that's why we try to tune the crystal structure itself. So one case is the structurally left-handed, another case is the right-handed crystal, and we wanted to do RPS, as Neil showed that if you just do a left-handed, right-handed crystal, the topological states itself change. So how to do how to control way to tune the structural chirality. For that, we use the seed. So this cobalt doping is already known in literature that until 10% say this cobalt doping, this say Fe.9 CO.1 SI is left-handed chiral crystal. So that's why just take these crystals and grow these. So it's not like PDGA was the target. So PDGA was selected because the seed melting, so it's the most suitable one to grow the chiral crystal. See, the COSI, RHSI, it is not possible to grow this crystal growth because the seed melting temperature is much lower.
So if you use just the cobalt silicon or just the iron silicon, what did you get as a seed?
See, cobalt silicon, I don't have left-handed right.
No, I mean, okay, so if you grow the sample, there is no chirality.
Of course, there is a chirality, but it will be either left-handed or right-handed. You will not have the control.
I see. Got it. Okay.
So we wanted to have same compound, but two pieces. One is left-hand, one is right-hand. So that's why that's what I told. This is the forced crystal growth with the seed.
Niels.
I have a question about the updated CPGE figures. So you say you don't reach channel number 4 because you get additional corrections?
See, that's what I said. There is a shading of M point contribution.
Right. So did anyone try to quantify the corrections from the sort of quadratic bands and this endpoint?
That I don't know.
Yeah.
I think this is actually Professor Joseph Weinstein is already working on this, I think. So let's see.
So let's thank the speaker again and